So what we're going to do is going to start off by looking at this guy on the treadmill. Now, we're going to link back to a few different topics here, so keep on the ball. So thinking biology first. What chemical reaction is going on, allowing him to run on the treadmill? Hopefully, he said respiration. Okay, so now linking back into energetics, so energy changes. What kind of reaction is respiration? Hopefully, you're saying it's an exothermic reaction. Good, keep that in your mind. So, when it's really cold, what do? Yeah, we shiver. Okay, so we start generating movement, okay, to generate heat. Okay, so this exothermic process of moving allows us to generate heat to keep our bodies stable in terms of temperature. Okay, called homeostasis, regulating body temperature. So that is kind of like equilibrium, isn't it? Yeah, because that's what we've been looking at. So for this guy, what will happen if we cool down the room that he's in? Hopefully, you're going to say, well, he's going to increase respiration. So how's he going to do that? By moving quicker. Okay, so he's going to speed up. Okay, so his equilibrium is going to shift a little bit. So what will happen if we heat the room? Well, I know for me, when it's really hot like it is at the minute, I kind of slow down. I don't go as quickly. So I'm changing. My equilibrium is changing. It's producing less heat in my body so that I'm staying constant. Okay, I'm staying in equilibrium. Now, what we're going to do today is we're going to look at a few different things. We're going to look at a thing called Le Chatelier's principle, and we're going to look at factors that affect equilibrium, okay, or the position of equilibrium. Because if you remember, when we had our escalators, so equilibrium could be at the top, all products, so it could be at the bottom, mostly reactants, or it could be somewhere in between, any combination of them. So we're going to be looking at that. And we're going to try and apply our understanding of Le Chatelier's principle and equilibrium to predict changes that will occur. Okay, so Le Chatelier's principle, what's this all about? Well, it is this guy, Henri Chatelier. You don't need to remember anything about him other than his principle and be able to apply it. So what his principle is all about is that a system in dynamic equilibrium will move the position of that equilibrium to oppose any change put on it. Okay? So if we make something hotter, the equilibrium is going to shift to try and get rid of that heat. Just like the guy in the treadmill. If we make it colder, he's going to speed up to make more heat. If we make it hotter, the guy on the treadmill is going to slow down to try and reduce heat. Okay, we can apply this to our reactions. So one of the easy ways is by looking at temperature changes. Now, imagine I've got an endothermic reaction like this one. Now, we can see that it's endothermic. What tells us endothermic? Well, it's that positive charge next to that enthalpy change. So we know it's an endothermic reaction. And I like to sort of think back on these in terms of a common reaction that we're familiar with. Okay, thermal decomposition. We've got a reaction, say I've got calcium carbonate. I'm going to heat that calcium carbonate up, and what happens is I produce my carbon dioxide and my calcium oxide. So I know that's endothermic. I need to put heat in there to make it happen. So that reaction, if I increase the heat, it goes to the right hand side, it forms the products. So it's the same for these other reactions. So just like this one. So I increase the temperature, the equilibrium will shift to the right to get rid of the heat. Remember, as with that reaction happens, it's taking in energy. So that energy is taken in from the surroundings, it's cooling the surroundings down. So that's the change that it's opposing, is the heating up, and it's cooling it down. Okay, so what happens if I cool this reaction down? Well, the equilibrium will shift to the other direction. because remember, it's a reversible reaction, so that if I cool it down, it will favour the opposite reaction, okay, the exothermic one, which is exactly the same but the other way around. Okay, so key it into your heads. Remember, an increase in temperature favours the endothermic reaction. So just drill that into your head, and then you can use that to apply it. Okay, so let's apply this to a different reaction. So this time I've got hydrogen and iodine making hydrogen iodide. Now we can see that the forward reaction is exothermic. Why? Because I've got that little negative sign in front of my enthalpy data, my minus 9.6 kilojoules per mole. So that means that every hydrogen molecule and every iodine molecule react together to form two hydrogen iodides, releasing to the surroundings, making the surroundings hotter, 9.6 kilojoules for every mole. So what happens if we start fiddling about with the system in equilibrium of this reaction by changing the temperature? Well, if I increase the temperature, what's going to happen? Well, the reaction in the forward direction releases energy. Okay, it releases heat as it is. So it's not going to want to do that. It's going to want to oppose that change. So what's it going to do? It's going to favour the opposite direction. So it's going to go in the endothermic direction. So those hydrogen iodide molecules will then fall apart and then reform hydrogen molecules and iodine molecules in the reverse direction, because that's going to take in energy for that to happen. So it's going to try and keep that equilibrium balanced. So another example. This time we're going to be looking at the reaction of nitrogen and hydrogen to make ammonia. Now you will become quite familiar with this one because it's a common example that's often used, and you will come across it next year in one of the subjects there. So we've got nitrogen, we've got hydrogen, and it forms ammonia, NH3. Now it says, let's have a look at the question here. Which direction is endothermic? Okay, so we're just identifying that first. Okay, well, it gets colder in the backwards direction, so that must be the endothermic direction because the surroundings get colder. Which direction do reactions move when heated? Well, what they're going to do is they're going to move in the endothermic direction. So if we heat them, they're going to move in the endothermic direction, which is backwards. So the equilibrium will move from the ammonia to the nitrogen and hydrogen. So the equilibrium shifts to the reactant side of the reaction. Will heating give more or less ammonia in the equilibrium mixture? Well, we're heating it, the equilibrium will shift to the left, so I answered my own question before, didn't I? So, no, it won't. It will give less ammonia in the equilibrium mixture. Right, so this time what we're going to look at is the effect of pressure. So before we get into what the principle of Le Chatelier's is when we come to this, well, we've got to think about what pressure is all about. Okay, what is pressure? Well, it's the number of collisions that's occurring on a surface.
The independent gas particles inside a slightly deflated basketball collide with one another and the walls of the basketball, causing pressure. How could you raise the pressure in the ball? You could add more air particles to the ball. As the number of particles increases, so does their number of collisions per second with the wall of the basketball, which first pushes out the walls of the ball and then raises the pressure.
So if I had a bike tyre and I had it just flat, there's not many collisions on it. What do? I increase the pressure by putting more air molecules into it to increase the pressure. So there's more collisions on the surface supporting the tyre. So we're going to have a look at some examples on this now. So we'll revisit ammonia. So here's the equation again. And we can see that we've got 1 mole of nitrogen, and that's reacting with 3 moles of hydrogen, and they form 2 moles of ammonia. So 1 nitrogen, 3 hydrogens, that's 4 moles of gas on the left-hand side. The right-hand side of the equation, on the product side, we've got 2 moles of ammonia. Okay, so we see 4 on one side, 2 on the other. So there's more molecules on the left-hand side, on the reactant side, than there are on the product side. Okay? So if we increase the pressure, we're squashing more particles in the same volume. What's going to happen to the equilibrium? What does Le Chatelier's principle say? It tells me that the position of an equilibrium is going to shift to oppose the change. My change is more pressure. It wants less pressure. It wants fewer collisions on any surface. So what is it going to do? It's going to move to the side with fewer molecules, with fewer moles of gas. So in this case, for our reaction to form ammonia, that's going to be on the product side, where we've got 2 moles of ammonia rather than 4 moles of reactants. It doesn't matter what those molecules actually are, it's the total number of them, or the total number of moles. That's the important thing. Right, so now I'm going to have a look at concentration. Concentration is very, very similar to pressure, which we've just looked at. So what's going to happen to a system if we start messing about with concentration? But what is concentration to start with? Well, it is the number of particles of whatever you're interested in within a unit volume, per decimeter cubed or whatever it is. Okay? So thinking back to what Le Chatelier's principle tells us, we've got some reactants, we've got some products. We're going to change the concentration of one of these. What's going to happen? The equilibrium is going to shift to oppose that change. If I take something out, Le Chatelier tells us it's going to try and make more of it because we've taken it out. If we put more of something else in, it's going to want to try and get rid of it by whatever means it can. So if I have some reactants and I increase the concentration of my reactant, then it's going to form more product to get rid of it. So it will shift the equilibrium to the right-hand side. If I then start taking out some product, what's going to happen? Well, it's going to oppose that change by trying to make more of that product. Okay, the final key thing on this is just really what happens with catalysts. How do catalysts affect the equilibria? Well, the very short answer is they don't. Okay, catalysts have no effect on the position of the equilibria. Remember what catalyst does? It provides an alternative reaction pathway with a lower activation energy. So all it means is that the reactions happen faster. But which reaction happens faster? Well, it's the forward and the backward reaction. Okay, all it means is that equilibrium will be established sooner. That's the only thing. Okay, there is no effect on the position of equilibrium.